Hi everyone. Today we will continue with the Fourier series. Last time we learned how to compute the coefficients when you know the existence of a Fourier series for a given function. And along the way we learned that, actually if you are going to find a Fourier series of a function, that function has to be periodic, but we didn't know all the conditions. So now the following theorem, the Fourier Convergence Theorem, will basically tell us everything we want. Okay, so now let me state it, and then we can do some examples of it. So Fourier Convergence Theorem. So what does it say? So first of all, for which functions then we may have Fourier series? So it says the following. Suppose f and f prime, its derivative, are piecewise continuous. Piecewise continuous. On minus L to L. So on a two-length interval it is continuous, piecewise continuous. What does it mean, piecewise continuous? It's continuous everywhere except certain points, and at those points we allow removable discontinuities or jump discontinuities. No infinite discontinuities. So we have the functions f and f prime continuous, piecewise continuous on the given interval minus L to L, and outside of this, it is periodic. So f of x plus 2L is equal to f of x. So that means if you know the functions here, then you know everywhere by using this notion. So it is 2L periodic. Then if these conditions are satisfied, then f of x has a Fourier series. I will use the following notation. It's not used in the book, but just to distinguish the function with the series. So then f of x has a Fourier series. I will write the following: SF. Okay, SF. So you can think Fourier series of the function f, which is equal to a0 over 2 plus n from 1 to infinity a n cosine n pi over Lx plus bn sine n pi over Lx. Okay, so it has a Fourier series of the following form. Moreover, this is the crucial part. Moreover, f of x is equal to SFX. So this means the Fourier series, the number you will get from the Fourier series is actually the same thing as the number you get from the function. When x is a continuous point. What I mean by a continuous point, when the function is continuous at x. Okay, when your function is continuous at f, so at x. In other words, f is continuous at x. So they are equal to each other. The number you get from the Fourier series and the number from the function are equal. How about this continuous point? If f is discontinuous at x, but we know that since it's a piecewise continuous function, it has only either removable or jump discontinuity. Actually, removable is not a very bad discontinuity because you can fill the hole and you can make it continuous. The problem is basically about jump discontinuity. So if f is discontinuous at x, then the number you get from the Fourier series is equal to, I'm using the book's notation now, fx plus fx minus divided by 2. So what are these things? What is fx plus? What is fx minus? So this is the left limit at x, and this is the right limit. This is the right limit at x. I mean, if they were same, of course, if they were same, we would have a limit there, and the function is, if the function is defined there, it will be continuous, I mean, as the same. So if the right limit and left limit were same, and if the function has the same value there, then you will get a continuity. Automatically, you fall in the first case, the Fourier series and the functions give you the same answer. But here, if they are not the same, if the right limit and left limit are different, automatically you will not have continuity. So in this case, the Fourier series will give you a number again, but that number will be just the average of the right and left limit. So obviously, I mean, if these numbers were same, if the right and left limits were same, then you basically get f of, so you just get the, I mean, their average value. If that is also equal to the function's value, automatically you get the first case. So the Fourier series and the function value are same. So in this case, you get the average of the right and left limit. Now, I want to do an example for this. All right? So, but before that, let me remind you, so our function is periodic, and if you look at the Fourier series, like if you just use this, that's also periodic. And what is the period? Again, all these functions have different period, but there's a common period, which is 2L actually. So here, also this SF, the notation I'm using here, which is the Fourier series of the function, then also it's a periodic thing too. All right. Now, let's look at the following example. So from what I'm raising, if you want to summarize what this theorem says, if your function is, and its derivative are piecewise continuous, and if your function is also periodic, then definitely it will have a Fourier series. Okay? So the conditions are actually not very, very strong, other than just the periodicity. I mean, it's a strong condition, but f is continuous, f prime is continuous. If you think about the power series, I mean, then your function must have all the derivatives, and at least so, and also even in that case, you may not have a power series. Your power series may converge to something else. But in this case, it says that your function is continuous if f and f prime are piecewise continuous, and if your function is periodic, automatically you will have a Fourier series. All right. Now, let's look at the following function. F of x is given as this way. So between minus 1 and minus 1 over 2, it is minus x. Between x minus 1 over 2 and 0, it is 1. Between 0 and 1 over 2, it is 2x. And between 1 over 2 and 1, it's x minus 1 over 2. So I just gave you what's happening between minus 1 and 1, and also I'm adding, if you look at minus 1, 1, like minus L, L, so its period is 2. All right, so now if you look at this function is a periodic function with period 2, and it's a piecewise continuous function because all these functions are continuous, but we don't know what's happening at the endpoints, but I mean, they are not going to infinity there, so as a result, this is a piecewise continuous function, which is periodic. So by the Fourier Convergence Theorem, it will have a Fourier series. And now, the question is, compute the following. Compute the value of the Fourier series at 1 over 2. Compute the value of the Fourier series at 1 over 4. Compute the value of the Fourier series at 17.5. Compute the value of the Fourier series at 41.3. So compute the values of the Fourier series at the given points. All right. Again, I mean, I want to, so it's periodic as you can see, and all these things, all these functions you see are continuous functions in the open intervals, and over the, at the boundaries, we don't know what's happening. So let's see the picture before we continue with the computation. How does the graph of the function look like? All right. So c minus x, okay. Zero, 1 over 2, 1, minus 1 over 2, minus 1. So this is just one period. So let's stand it. So this is 3 over 2. This is 2. This is 5 over 2. This is 3. So it goes like this. And here we have minus 3 over 2, minus 2, minus 5 over 2, minus 3, and goes like this. So if you look at the graph, now, between 0 and 1 over 2, it is 2x. So if you plug in 0, you get 0. If you plug in 1 over 2, you get 1. So it's like this, and this is not included. So this is included. So this is what we have. And this value is 1. And between 1 over 2 and 1, it is x minus 1 over 2. So if you plug in 1 over 2, then you get 0. If you plug in 1, you get 1 over 2. So we have this point and this. If you plug in 1, we get 1 over 2. This one, okay, and this value is 1 over 2. And if you look at between minus 1 over 2 and 0, we have 1. So it is 1. So it's like this. And between -1 and -1/2, it's minus x. So if you plug in -1, you would get 1. If you plug in -1/2, you will get 1/2. So we have exactly like this. And minus, so it's this one. Which one is included? 1/2. So, okay. So this is the graph. This is the graph between -1/2 and 1. As you can see, we have a jump here, we have a jump here, we have a jump here. So, and that's what we have. So then, how will I draw the rest? Actually, I will just use the periodicity. So I will just copy and paste the picture here. So I will copy this picture. And if you look at it, I just take it and move here. So we have like this. This is included. Take and move here. And then we have this piece here. And we have this piece here. Similarly, now you want to get this portion. So what we need to do, so take this and move it here. So we will have the following. Okay, so now take this and move it here. And now this one. And now this one. So this is what we get. So it continues like this. Okay. Now, as you can see, this function is periodic with period 2. It has jump discontinuity, so it is automatically piecewise continuous. So if you take its derivative, and derivative of this portion is 0, derivative of this portion is 2, and so you have, again, just constant functions as derivatives. And so you only have jump discontinuities. So as a result, this function will have a Fourier series. So then, how about the values above? So now I want to compute the first one, the Fourier series value at 1/2. So now I look at the 1/2. So 1/2 is here. Is it a continuous point? No. So that means that I have to look at the right limit and left limit and take their average. So this is my explanation. 1/2 is this continuous point. So I will look at the right limit plus, I will look at the left limit minus, and divide by 2. So if you look at the right limit, its value is 0. If you look at the left limit, its value is 1. And so if you divide by 2, then we get 1/2 again. Okay. Okay. How about 1/4? Let me just do it here maybe. Now if you look at 1/4, 1/4 is here. So here your function is obviously continuous. And so that means it will be equal to 1/4 of f. So I'm writing now x equal to 1/4 is a continuous point. And so what is f of 1/4? 1/4 is between 0 and 1/2. Between 0 and 1/2, the function is 2x, so 2 times 1/4 is the answer. So that is 2 times 1 over 4, which is equal to 1 over 2. Okay. Now, the others. Let me just do, okay, maybe this one, and leave the last one as an exercise to you. So, let me just do it here. Okay. So why don't you do the negative version, like minus 41.3 as an exercise? I mean. Okay, so how about F 17.5? How about this? So I'm checking the 17.5. It is not in my picture. So I cannot say anything from the graph, just drawn here. But I know something further. My function is periodic. So if I move it 2 units, 2 units, 2 units, I always get the same value. So that's the reason, like, I mean, if you look at what we are doing here, we are copying and pasting, pasting, pasting. So that's the reason we have similar pictures later. So then, how can I compute this thing? So if I subtract 2 from this, I will get the same value. If I subtract 4 from this, I will get the same value. If I subtract 6, I will get the same value. So what I'm doing, I'm just subtracting multiples of my period. So now my period is 2. So which multiple will put me in the picture drawn here? So if you look at, I know the graph between minus 3 and 3. If I can just come in this picture, then it's automatically fine. So, for example, if I multiply this thing with 10, it's perfectly fine. I will fall in the picture. But if you want to fall in this part between minus 1 and 1, then what you can do, you can multiply with 9, then what do we get? We have 18 here. This is 17.5. So then it will be the same as that 17.5. So this is the value at minus 1 over 2. So because 18 minus 17.5, we get negative 0.5. So it's what we have. So now if you look at minus 1 over 2, we are here. And also if you look at, we are here. So right limit, left limit, they are not same. It's a jump discontinuity, so I have to take their average. If you look at the average is the mid value here. So it is F minus 1 over 2 plus F 1 over 2 minus divided by 2, because minus 1 over 2 is a discontinuous point. Okay? So if you look at this thing, so minus 1 over 2, right limit is 1. Left limit is 1 over 2 and y by 2. So you get 3 over 4. That's the value. So for the last one, 41.3, or you can take minus 41.3. So then you can just, again, do the same thing to find the values. All right? See what we have. All right. So now we know when we can find a Fourier series. And how about how do we compute the coefficients? Actually, we know how to compute the coefficients, and let's remember them. Maybe let's write it. So the coefficients are computed via this Fourier formulas or Euler Fourier formulas. So what were they? So we had A0, so AN was 1 over L from minus L to L. f of x times cosine n pi over Lx dx. So this integral will give you the coefficient n. So when n is 0, if you look at a special case, then this is from minus L to L. Okay, and integral of the function, because cosine 0 is 1. So actually, when you are writing, we know that you write a0 over 2. So basically, you have to divide by 2, which means you have to divide by 2 here, which tells you you are actually the first term, the constant term of the Fourier series is the average value of your function between minus and L. So this is twice the average value, but in the Fourier series, we are writing a0 over 2 because we want to use the same formula. And for Bn, we had 1 over L from minus L to L, f of x times sine n pi over Lx dx. So we are using this formula to compute the Bn coefficients. All right. Now, we can start doing examples of Fourier series. All right. So our question will be compute the Fourier series of given functions. And the first example is the following. F of x is equal to 0 when x is between 0 and 1. Actually, yeah, why not? Let me just change the problem a little bit. Okay, minus 2 to 0. And when x is between 0 and 2, it is 1. Okay, so I was planning to do period 2, but now this is the same thing with period 4, because I gave you between minus 2 and 2, so now this thing says that your period is 4, so this function is obviously piecewise continuous. So if you look at its graph, so it is 0 here, and it is 1 here, 0 here, because I'm just shifting, 1 here, its value is 1, 0, and 1, and 0, and 1, so vice versa. So you can think like this is like a signal again. So your signal becomes 1, 0, 1, 0, 1, 0. So it's going like this. So it's piecewise continuous. Its derivative is 0 everywhere except at even integers. So they are both piecewise continuous, periodic with period 4. So it will have a Fourier series. Now let's find its coefficients. So we'll start with an. I will be lazy, and so I will use this thing here. So what is L here? As you know, 2L is our period. So 2L is our period. L is just half of it. Our period is 4, so this number L will be 2. So I need to integrate from -2 to 2. And n pi over L, again, L is 2. This is what we need to do to compute the an. How about a0? a0 is 1 over 2 from 2 to 2. Actually, I mean, we can do a0 very easily because it's just the integral of the function from -2 to 2. So it's all about the area. So I need to compute this area and divide by 2. So if you look at the area, base is 2, height is 1. So this area is 2. This is 0. So this integral is 2 divided by 2. So we get 1. Okay. So now how about this now? If you look at our function as piecewise continuous, so I need to write the integral from -2 to 2, but I know something about my function. My function is 0 between -2 and 0. So that means the product is 0. So I just need to compute. Maybe let me just write first. So if you write the integral from -2 to 0, cosine n pi over 2x dx, plus from 0 to 2, cosine n pi 2x dx. Between -2 and 0, my f of x is 0. Between 0 and 2, my f of x is 1. Okay? So this part is completely 0. So it's all about computation of this one. So then we get 1 over 2. So antiderivative of cosine is sine n pi over 2x divided by n pi over 2 between 0 and 2. So if you look at this, this is 1 over 2. And when you flip this, we have 2 over n pi and parentheses sine. If you plug in 2 here, 2 cancel, sine n pi minus, if you plug in 0, we get, wait a minute, did I make a mistake somewhere? Okay, no. Sine n pi and sine 0, this is what we get. So sine n pi is 0, sine 0 is 0, everything is 0. So it says that all the ANs except a0 is 0. And this is what we have, which is 1. All right, now Bn. So Bn, now which is 1 over 2 from -2 to 2, f of x times sine n pi over x dx. Similarly, between -2 and 0, this function is 0. So it's all about integration from 0 to 2. So let me just skip that middle step there. We have 1 over 2, the integral from 0 to 2. So this is equal to this one because between -2 and 0, your function is 0 because of that. Okay, so and of our function is 1 sine pi over 2 x dx. So if you look at this, we have 1 over 2 antiderivative will be negative cosine n pi 2x divided by n pi over 2. And the boundaries are from 0 to 2. So if you now write this, 2's are cancelled. We have now minus 1 over n pi. Flip 2 over n pi, 2 cancels. We have 1 over n pi. Inside, we will have, if you plug in here, I took already negative out. So we have cosine n pi and minus cosine 0. This is what we have. But now, if you look at cosine n pi, cosine, so n is now, we know, starting from 1, cosine pi is minus 1. But if you like, n is 2, cosine 2 pi is 1, cosine 3 pi is minus 1. So that means this is always minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, depending on the parity, evenness and oddness of n. So if you look at this, I can write this thing minus over n pi. This is minus 1 to the n, because when n is odd, it's minus 1. When n is even, it's plus 1, minus cosine 0, which is always 1. So what do we get from this? When this is 1, 1 minus 1 is 0. When this is minus 1, we get minus 2. So for the even terms, we get 0. For the odd ones, we get negative 2. And since there's another negative here, we get 2. So what can we say about this? This is equal to 0 when n is 2k. When n is even, we get 0. When n is 2k minus 1, so this means odd, k starting from 1, then we have 2 over n pi, and n is 2k minus 1. So n, let me just write this, 2k minus 1 times pi. It's exactly n pi. So if you write this, and then if you write this, so the Fourier series of this function is equal to, now a0 was 1 over 2 divided by 2 plus, now we don't have any an's anymore, and we just have bn's, so n starting from 1 to infinity. So bn's, what are bn's? Or if you want, you can write here k, or then you can convert it to this one. So we have 2 over 2k minus 1 times pi, and sine n pi, n is now 2k minus 1, 2k minus 1 times pi over L, which is 2x. So it's what we have here. So this is your Bn. So I just took the non-zero terms, and because the others are all 0, so that's the reason, like, we have here all odd ones. Even ones disappear because their coefficients are 0. So this is the Fourier series of this function. Okay, now second example is the following. So f of x is equal to x. But when x is between minus 1 and 1. just take this function x between -1 and 1, but then make it periodic. Okay, this is what we have. So this is the function. So if you draw it, so it's the x function, so this function, okay. And then, now copy and paste it to the other intervals. So we have 2, 3, 4, 5, -2, -3, vice versa. So copy and paste. So what we get is this. Okay. So it goes like this. So this is the function we are talking about. It's a piecewise continuous function. We have jumps at -1, 1, 3, 5, vice versa, at odd numbers. And it's piecewise continuous. Its derivative, if you take derivative of x is 1, so we have constant. So it's piecewise continuous. It's periodic, so we will have a Fourier series for this function. Now, let's compute its coefficients. All right, now, first ANs. So what is AN? So in this case, we have 1. From -1 to 1, actually, these numbers tell you what you need to write here, 1. So L is 1. So f of x is x. We have cosine n pi over 1 x dx to compute this one. There's one thing you should probably have noticed here. It's not like the previous one, because in this graph you see some symmetry here. So this function is an odd function. It's an odd function because its graph is symmetric with respect to origin. So that means our function is odd. So this is odd. So cosine is an even. Then their product is odd. So for an odd function, on a symmetric interval from -1 to 1, the integral is always 0. You can do this for, if you want a 0, it's similar. So this is going to be 1, which is an even function. So you get 0. So that means we don't have any cosine terms. We just have sine terms. Right? So why is this happening? Actually, because our function is an odd function. It's an odd periodic function. And from this example, we can conclude the following. For an odd periodic function, we will have a sine series. As you can guess easily, for an even function, we will have a cosine series. I will leave the exercise for you. All right, now this is now 1 over 1. From -1 to 1, we have x times sine n pi over 1. It's dx. Okay. So this time, odd, odd. Their product even. and the product is even. So one nice thing about evenness, I mean, it doesn't bring you too much, but at least, I mean, you can just integrate from 0 to 1 and you can double it. So this will be equal to 2 times the integral from 0 to 1 x times sine n pi x dx. But we cannot escape from the computation. So we have to compute this. This is a polynomial, this is trigonometric. So we have to use integration by parts. So if you use the following integration, so you use polynomials come first. So we will say u is equal to x. So du is automatically dx. dv is equal to sine n pi x dx. So v is equal to negative cosine n pi x divided by n pi. Okay. So with this now, we have 2 times u times v, which is negative x times cosine n pi x over n pi minus, so this is already computed from 0 to 2, and we have now u times dv, so we have now v times du. But there's a minus here, there's another minus, so it makes it plus. From 0 to 2, we have cosine n pi x over n pi dx. Okay, now we continue with this computation. Okay, so we can integrate. So minus x cosine n pi x over n pi, and entire derivative of this thing will be sine n pi x over n pi. There's another n pi here. We have n pi squared from 0 to 2. What we have. So if you plug in 2 here, you plug in 2 parentheses, we have 2 n pi, and we have 2 here. So we have minus 2 times cosine 2 n pi over n pi. If you plug in now 2 here, 2 n pi at multiples, so we have 2 n pi, so multiples of 2 pi, so there we will have 0 for sine. Okay, this is when you evaluate at 2. Now minus, now we evaluate at 0. So when you evaluate at 0, this time we have x is 0, so this is 0. Plus, and when you plug in 0 here, sine 0 is 0, so this is what we get. And so this is going to be negative 4 over n pi. And now we have cosine 2 n pi. So we have cosine 2 pi, cosine 4 pi, and so it's automatically, 1, because you are multiples of 2 pi. So this is what we get as the result. So okay, so then we just have this Bn. So if you write the Fourier series, that's just m from 1 to infinity minus 4 n pi and sine n pi x. This is what we have. Oops. Oh, okay. Oh, sorry. I made a very stupid mistake. I was checking why with a different answer, so I'm sorry. So this is from 0 to 1. So I just remember the previous example. Sorry. This is from 0 to 1, 0 to 1. Sorry for that. So this is from 0 to 1. Okay, so this is n pi. So this is n pi, okay? And this is n pi. And still, we are getting, when you plug in 1, now we are getting cosine n pi times minus now 1. When you plug in 1 here, sine n pi is always 0. Now you plug in 0, we have 0 here. And we plug in 0, we have 0 here. So this is going to be minus 2 n pi times cosine n pi. And cosine n pi is now, so again, at multiple, even multiples, it will be plus. At odd multiples, it will be minus. So we will have minus 1 to the n. And so this part will be, sorry for this stupid mistake. So we will have, now I can just take minus inside. So we have minus 1 to the n plus 1 times 2 over n pi times sine n pi x. That's what we have now here. All right. Let me write an exercise for you, which is similar to this one. Exercise. Do the following. So f of x is equal to absolute value of x when x is between minus 1 and 1. Actually, you can take equality here with fx 2 is equal to f of x. So this time, this function, if you look at it, it's v-shaped. This is a symmetric graph again, which is now an even function. So this time, I mean, you will see that there won't be any sine terms, just the cosine terms. Do it as an exercise. It's very similar to this one. Okay. Now, what we learned basically how to compute the coefficients of the Fourier series for a piecewise continuous function which is periodic. And also we learned something. If our function is an even function, we will have just cosine series. If our function is an odd function, we will have just sine series. I will do 2 more examples and then finish today's lecture. Oops, now, we were going with an order, so let's take 3. So, take the function sine square x, okay? And the interval, let's take between minus pi and pi. Okay, so this function, and I got it, this one. So I'm just taking sine square function on the interval from minus pi to pi, and with period 2 pi. How are we going to do this? Actually, you can do by yourself. You can just directly apply the formulas. But there's an intention in this question. And so, as you remember, like this notion from power series, so what was the idea of the power series? You want to express a function as an infinite polynomial. You want to express as an infinite polynomial. If your function is already a polynomial, so its power series will be, again, a polynomial. But if you just compute the Maclaurin series, it will be itself. So a Maclaurin series of a polynomial is itself. So because you want to express a function as a polynomial, if your function is already a polynomial, so then they must be same because there is a unique power series expansion. Again, here, when we have a function which is periodic, we will have a unique Fourier series because its coefficients are coming from the Euler Fourier formulas, the ANs and BNs. So now I want to express this function as a Fourier series. So how will be the form of the Fourier series? So if you want to write this Fourier series, it will be of the following form: a0 over 2 plus n from 1 to infinity, we have an cosine n pi x divided by L. But what is L in our case? L is exactly half of the period, which is pi. So if you do this, so these pi's are canceling, which means that you need to write it in the following form. Okay. So its Fourier series will be this one. So somehow, by using some magic, by using some formulas, if you can express sine square as this way, which means in terms of cosine nx and sine nx, then it's perfectly the Fourier series. And we know the following formula. Remember? Sine square x, the double angle formula. So this is, let me just remember and how you make it. Cosine square x minus sine square. We know that this is cosine 2x. And if you write 1 minus sine square in the place of cosine square, so we get 1 minus 2 sine square. So take sine square this side, cosine 2x this side, divide by 2. So then what do we get? We get the following. Sine square is equal to 1 over 2 minus cosine 2x. So this is what we have. So I was able to write sine square as this way. So if you look at now, in this expansion, if I take a0 as 1, so then I catch the constant term. If I take cosine 2x, cosine nx, if n is 2, then I get cosine 2x. So if I take a2 as minus 1 over 2, and all the others are 0, otherwise 0. So in this expansion, take a0 as 1, a2 as minus 1 over 2, and all the others are 0, basically you just get this, which is the Fourier series of sine square. So no computation needed, as long as you can express it this way. So you know how to express it this way, then you will be able to get it. But now, be careful, I mean, not whenever you see like sines and cosines, oh, I will be able to find it by using expansion. It's not always true, be careful, I mean. So they must match. What does it mean, match? So if you look at the expansion, you have cosine nx, sine nx. So like multiples of x, 2x, 3x, 4x, 5x. So it's the reason you are doing this. If I change the problem like this, the same function, but the interval is now from -1 to 1. This time, my period will be 2, my L will be 1. So if you write the expansion, you will have a n cosine n pi over 1x, which means you will have multiples of pi here. Cosine pi x, cosine 2 pi x, cosine 3 pi x. But your formula is still same. There is no pi here, which means that you will never reach such an expansion. So in that case, unfortunately, you have to use the formulas of a n and b n's. But here, you can escape from the formulas because the coefficients, like here, the inside the frequencies match. And so, but for this one, they won't match because you will have pi here, no pi's in the formula. Unfortunately, you have to do the computations. Okay, so one final thing. Number 4, something similar to the above thing. F of x is equal to 1 over 3 sine 3x minus 2 over 5 sine 5x okay, and we have, it's true when x is between minus pi and pi. Okay. So it seems very similar to the previous problem. Let me just change the nature of the problem a little bit. Okay. Let me make it 4x. Let's say this is 10x. And this is minus pi over 2 and pi over 2. Right? So let's do it this way. And its period is now pi. How about this one? Again, we have a sine function. So at first, I mean, if you want to escape from computations, and let's look at whether I can express somehow, this is the Fourier series of the original function. So let me just first of all check. If I had the Fourier series of this function, what kind of expansion I will have? So if you look at now SF, this will be a 0 over 2 plus n from 1 to infinity, a n cosine n pi x over pi over 2. Okay, so what we have now, pi's are cancelled when you flip. This is just becoming 2n. Okay, 2nx plus bn sine 2nx. This is what we had. All right. So it says that in the expansion you will have even integer multiples of x. So as you can see, like x even integer, x even integer. So it means I can make some matching and I can find the coefficients without doing any computation. Furthermore, you can easily see the following. I have just sine function, and sine function is an odd function. So in the expansion, actually, we will not have any cosine terms. So no cosine terms. It means it will have just sine terms. So if you look at, now I can just do some matching here. So if I take, so all an's 0, so that means now no cosine term in this expansion. And if I take a, so b2 equal to 1 over 3. So if you look at the b2 now, if this is 2, inside will be 2 times 2x, so it will be 4x. So I will catch sine 4x when n is 2. And so if I take b2, 1 over 3, I will be able to get this term. Similarly, if you take b5 as minus 2 over 5, then 5, this is 10x, so I will catch this term. So then I will be able to write n these parts. And the rest must be automatically 0. Otherwise, bn is 0. So that if you write this way, then automatically this expansion will give you this expansion. So you will be able to find the Fourier series of the given function. So we didn't do any computation. We are just using the idea of the Fourier series. We are trying to express our function in terms of sines and cosines. So it's already sine. So we try to now express with this thing in this way. So if the frequencies somehow match, so these numbers are frequencies 2n, 2n. If they somehow match the numbers here, then automatically that means that's the Fourier series. So in the previous example, as I said, if you cannot match, then unfortunately you have to do the computation. Okay, so I'm finishing here. In the upcoming lecture, so we will also learn how to compute the Fourier series of functions which are not given as periodic initially. So we will basically make them periodic, and then we will be able to compute their Fourier series. And eventually, we will solve the heat equation, and I will do one more example of a partial differential equation where we do all these details. Okay, see you next time.